Hello friends, this is Priyanka. Today we are going to solve a problem on second law of thermodynamics. Now first I will read what is the given question. A reversible heat engine operates between two reservoirs at a temperature of 600 degrees Celsius and 40 degrees Celsius. The engine drives a reversible refrigerator which operates between reservoirs at a temperature of 40 degrees Celsius and minus 20 degrees Celsius. The heat transfer to the engine is 2 megajoule and the net work output of the combined heat and refrigerator plant is 360 kilojoule. Find the heat transfer to the refrigerant and the net heat transfer to the reservoir at 40 degrees Celsius. So this was the given question. We will first draw the diagram as per given data. Here it is given that the work output from the heat engine is given as an input to the refrigerator. Now if we observe, heat engine operates between two reservoirs, that is the higher temperature reservoir and lower temperature reservoir. So we will first draw here the diagram for the heat engine. So higher temperature reservoir is at 600 degrees Celsius. So we will convert this into Kelvin, that is 873 Kelvin. I will draw here the higher temperature reservoir for the heat engine. So here we will say temperature T1. T1 is equal to 873 Kelvin. Now this is the heat engine. So we will draw here one line, and for the heat engine I will say here as a E, and the lower temperature reservoir will be at temperature T2. So this temperature T2, that is given 40 degrees Celsius. So for 40 degrees Celsius, that means we will take here as a 313 Kelvin. So I will take T2 is equal to 313 Kelvin. Now it is given that the work output from the heat engine is given to the as an input to the refrigerator. So again this refrigerator also works in between these two reservoirs, that is the atmosphere as well as space to be refrigerated. So again I will draw here the output from the engine is given input to the refrigerator. So I will draw here refrigerator R. Then again it is operated in between two reservoirs. Now if we observe the refrigerator, it operates between 40 degrees Celsius and minus 20 degrees Celsius. So here 40 degrees Celsius, that means 313 Kelvin. So this reservoir at temperature T2 is also at 313. So we have to show here the reservoir for, now this 40 degrees Celsius is the reservoir that is for atmosphere, where the heat is rejected from this refrigerator. So we will say that, I will say here will be temperature T3 and this will be the space to be refrigerated. So I will say space to be refrigerated. And it is at temperature minus 20. So minus 20, that means 253 Kelvin. So T3 is equal to 253 Kelvin. And the heat is getting rejected, that is extracted from this space and getting rejected to the atmosphere at 40 degrees Celsius. So next I will use here T4 is equal to 313 Kelvin. So from this we can say that T2 is equal to T4 is equal to 313 Kelvin. This is the layout as per given data. Now if we observe, the heat is getting transferred from this high temperature reservoir to the heat engine. So this heat transfer, that should be equivalent to this temperature T1 and that is equal to Q1. So I will show here the heat transferred from this high temperature reservoir, that is Q1. Then the work is done or work output is there from this heat engine and the remaining heat is rejected to the low temperature reservoir at temperature T2. So this heat transfer that should be equivalent to this T2. So I will say that this heat transfer, that is Q2. So what is the work done by this heat engine? That is this difference in between this heat Q1 and Q2. So I will say that WE is equal to, that is the work done by the heat engine, is equal to Q1 minus Q2. Now out of this total work output, some work is given as an input to the refrigerator. So this work input to the refrigerator, I will say that this will be WR. And the remaining work here, that is the combined work output, and that mentioned in the given question, that is the combined work output 360 kilojoule. So I will say W is equal to 360 kilojoule. Now we will move to the refrigerator. Now refrigerator works in between these two reservoirs, that is the space to be refrigerated at minus 20 degrees Celsius, that is 253 Kelvin, and heat rejected to the atmosphere at 40 degrees Celsius, that is 313 Kelvin. Now heat is getting extracted from the space to be refrigerated at a temperature T3. So what is the heat extracted? That should be equivalent to T3. So I will say that will be heat extracted Q3. Now input work is WR, and here refrigerator here work output to the atmosphere at 40 degrees Celsius, that should be equivalent to T4. And so I will say here Q4 is the output, that is the heat transfer to the atmosphere. So how we can write this Q4? So if we observe Q3 is the input, WR is the input, then Q4 is equal to Q3 plus WR. Now if we observe, it is given that heat transfer to the engine is 2 megajoule. So what is the heat transfer to the engine? That is equal to Q1 and 2 megajoule. So kilojoule is the standard unit. So I will write 2000 kilojoule. That is equal to Q1. And what we have to find out? We have to find out heat transfer to the refrigerant. So heat transfer to the refrigerant, that is equal to Q3, that we have to find out, and we have to find out net heat transfer to the reservoir at 40 degrees Celsius. So this is the reservoir at 40 degrees Celsius, and what is the net heat transfer? That is Q2 plus Q4. Q2 plus Q4, that we have to calculate. To find out Q3, we will first find out what is the work input to the refrigerator, that is WR. So for that, what is the maximum efficiency of the heat engine? So the formula is 1 minus T2 by T1. Now this T2 is known, T1 is known. So we will put the value in Kelvin, and which is equal to 0.6415. But we also know that what is the maximum efficiency? That is the ratio of output by input. So if we observe this heat engine, what is the output here? So output is work done, WE. And what is the input? Input is the heat transfer from this T1, that is Q1. So we can say that the work done by heat supplied, that is Q1 minus Q2 by Q1. So this Q1 minus Q2 is WE. So we can say that the work done is equal to, suppose we put the value of Nitamax is equal to 0.6415 is equal to Q1 minus Q2 by Q1, which is equal to WE, that is the work output from the engine, divided by Q1. So what is this WE? That is 0.6415 multiplied by Q1, and Q1 is given, that is 2000 kilojoule. So answer for the work output from the engine, 1283 kilojoule. Now we know that this total work output is supplied as an input to the refrigerator, and remaining is given the combined output, that is 360 kilojoule. So we can say that WE is equal to WR plus W. So if we put the known values, so here WE is known, then WR is unknown, and what is the W? That is 360 kilojoule. Then WR is equal to 923 kilojoule. Now we will move to the refrigerator. So here we have to calculate what is the coefficient of performance. So what is the formula for the maximum coefficient of performance for this refrigerator? That is T3 divided by T4 minus T3. So we will put the value because T3 and T4 are known. So here COP max is 4.217. So how we can define this maximum coefficient of performance in the other word? So it is the ratio of heat extracted from the space to be refrigerated divided by work input. So heat extracted is Q3 divided by work input is WR. So we can say that it is Q3 by WR. So if we put the value COP max 4.217, WR is also getting calculated 923, then Q3 is equal to 3892.3 kilojoule. So this is the answer of the first question. Then we will move for the next. Now we have to find out Q2 as well as Q4. Now if we observe this diagram, then this is the input Q3, then this is the input WR, then Q4 is equal to WR plus Q3. So we will calculate this. So Q3 is calculated, WR is also known, that is the work input, then 4815.3 kilojoule. Now we will find out Q2. So if we observe this work output from the heat engine, WE is equal to Q1 minus Q2. So WE is also getting calculated and then Q1 is known. Then it is easy to calculate Q2. That is Q2 is equal to 717 kilojoule. Now what is the combined heat that is getting rejected to the reservoir at 40 degrees Celsius? That is Q2 plus Q4, that is equal to 5532.3 kilojoule. And this is the answer of second question. Now we will solve the next problem based on the second law of thermodynamics for the heat pump. First, I will read what is the given question. A heat pump maintains a space at 22 degrees Celsius on a day when the outdoor air temperature is 0 degrees Celsius. The heating requirement of space is 1 lakh kilojoule per hour and power consumed by the pump is 5 kilowatt. Calculate the rate at which heat is extracted from the outside air and COP of the heat pump. Also calculate maximum COP. So this was the given question. We will first draw the diagram as per given data. Now if we observe, the higher temperature reservoir is nothing but the space to be heated. So space to be heated is at 22 degrees Celsius and we will convert it into Kelvin, that is 295 Kelvin. So I will say that this is the higher temperature reservoir, that is T1 is equal to 295 Kelvin. Then here is the heat pump. So we will write here as a P and the work input given to heat pump, that is WP. Then lower temperature reservoir. So lower temperature reservoir is the atmosphere and this atmosphere is at 0 degrees Celsius. So in Kelvin, if we convert this, then lower temperature reservoir is at 273 Kelvin. So T2 is equal to 273 Kelvin. Now how this heat pump works? So some heat is getting extracted from the lower temperature reservoir, that is from the atmosphere, with the help of the work input, and it is rejected to the space to be heated. So this heat is provided to here, that is space to be heated, and we have to maintain this space at 22 degrees Celsius. So here how we can draw here the heat transfer. So heat is getting extracted from the atmosphere, so which should be equivalent to temperature T2. So we will show here the heat transfer, that is Q2 is getting extracted from the atmosphere. The input to the pump is work input is WP, and with the help of this work input it is delivered or submitted to this space to be heated at a temperature 295 Kelvin. So here temperature is T1, so heat transferred should be equivalent to T1, that is Q1. Now next information is given that the heating requirement for space. So for this space, what is the heating requirement? 1 lakh kilojoule per hour. So we know that the standard unit is kilojoule per second or kilowatt. So we will convert this into standard unit, that is in kilowatt. So kilojoule per second, that is nothing but kilowatt. So how to convert this? So in 1 hour, this is the heat in kilojoule. So for 1 second, so in 1 hour there are total 3600 seconds. So we will divide here with 3600 and 1 lakh divided by 3600 kilojoule per second, and that is equal to 27.78 kilowatt. So this is the heating requirement for the space. So we can say that this is the value for Q1. So we have to transfer the heat, that is equal to 27.78 kilowatt. So Q1 is equal to 27.78 kilowatt. And work input is also given, that is equal to 5 kilowatt. Now what we have to find out? We have to find out the heat extracted from the surrounding or atmosphere. That means we have to find out here the value of Q2. Let us understand what is the difference in between actual COP and maximum COP. So when we have to calculate the actual COP, then we have to take the ratio of what is the heat transferred to this space to be heated divided by what is the work input. So because we have to take the actual values that are given. So here the actual values that are given, that is the heat transferred, that is Q1, and the work input, that is 5. So if we take these values, then we will get the actual COP. Then how to calculate the maximum COP, that is the maximum possible coefficient of performance. So for that, it depends on the temperatures of these two reservoirs, that is the higher temperature reservoir and lower temperature reservoir. So we have to convert these values, that is Q1 and WP, in terms of this temperature. So we know that this Q1 is equivalent to T1. So I will write here. So we have to take here, instead of Q1, that is T1, that we have to take this value for maximum COP. And instead of WP, we have to take this value in terms of T1 and T2. Now we know that if we observe this diagram, then this WP plus Q2 is equal to Q1. So this WP, I will write here, WP plus Q2 is equal to Q1. So how I can write here this WP? So WP is equal to Q1 minus Q2. Now this Q1 is equivalent to T1, Q2 is equivalent to T2. So we can write here as a WP is equal to T1 minus T2. So there is the heat transfer in between these two temperature reservoirs. So we have to take the value in terms of temperature, that is T1 and T2, to calculate the maximum possible COP. Now we will move for the first question, that is we have to find out the heat extracted from surrounding. So heat extracted from the surrounding or atmosphere is nothing but Q2. So from this diagram we know that WP plus Q2 is equal to Q1, because these two are the input to the pump and here is the output. So when we put the value, then we will get Q2 is equal to 22.78 kilowatt. So this is the answer of first question. Now what is the actual COP? So actual COP is heat transfer to the space divided by work input, or this heat input. So we have to write here as a work input. So 27.78 divided by 5, that is equal to 5.56. So this is the answer of second question. Now maximum COP. So maximum COP, that is the ratio of output by input. So here is the heat pump. So what is the output? That is we have to maintain the temperature for this space. So this is the output, is nothing but in terms of Q1, that is heat transfer, that is Q1, divided by input, that is the work input WP. So we have to take this in terms of temperature, that is T1 divided by T1 minus T2. So when we calculate this, so T1 and T2 are known, then this is the 13.4. So this is the maximum COP, and this is the answer of third question.